Hello guys, this is lecture 36. We are continuing with supervised learning, and right now we'll be learning about KNN, which is the K nearest neighbor algorithm. Okay, KNN means K nearest neighbor algorithm. This probably be a short video, but I'll try to explain all the nitty-gritties of it. It's one of the most least used algorithms, but it learns and leans heavily on the linear algebraical funda of dimensional distances or distances. Uh, and essentially, if you do this well enough, you understand a lot of other things as well. Okay. So again, it's a type of supervised ML learning algorithm, and it can be used both as classification and regression, mostly used for classification and predictive problems in industry. There are two properties. One is lazy learning algorithm. That means it does not have a specialized training phase where you pick a sample and all that. It uses all the training data while classification. Secondly, it's a non-parametric learning algorithm. That means it doesn't assume anything about the underlying data, and uh, it basically continues. So there are very limited number of parameters that can be used as such, and there are no underlying assumptions as well of linearity or any other thing. As long as the data is in any way numerically represented, it works. Okay. Now, these are some steps, but let's just say that you can basically understand this in this way. Okay, let me, yeah. So rather than going through the steps, let me, I think, make you help you understand them intuitively. So we have talked about this so many times that each data point has a row, okay, and each row has columns, and each columns add a dimension, okay, and it can be represented in n-dimensional plane by a point. Now imagine there are uh, two types of classes, okay, the knots and the crosses, and somehow they lie in the plane, some hyperplane. Now what happens is, if there are two classes, I would k is equal to 2, okay. That's why there are two classes and k is equal to and any number which we feel is feasible. For example, k is equal to 5 to begin with. Okay. And now what happens is the algorithm picks any data point. Okay. And sees the data points that are near it. Okay. Now this is the first data set is a training, a test case. Okay. Now what will happen? It will check for 5 nearest neighbors. So imagine 5 nearest neighbors are 1, 2, 3, 4, and 5. So 4 crosses and 1 dot. And it will, since the majority of them are crosses, this point should also be a cross. It's as simple as saying if your neighbors are rich, then probably your whole neighborhood is rich, and you live in a rich neighborhood. There's only one issue in it, which is also solved, and let me explain you. For example, k is equal to 5, okay? And I will explain this to you. Okay. Now imagine this k is equal to 5, and we are looking at this data point here. Now, if we take the 5 nearest neighbor 1, 2, 3, 4, 5, right? So there will be 3 knots and 2 uh, crosses. Okay. And if you see that towards this end, there are a lot of crosses and towards a lot of knots, and this probably would be a cross because it's very near to these two. So this approach would fail here. But imagine if we were taking an account for the distance as well. Okay. Now these two are very near and these two are very far. So these two are near and hence their weightage is way more than the far one. And then we would say this is a cross. Okay. Now this is a better approach because even anyway, if you're looking for nearest point, you will always calculate the distance from all the other points, right? So you will always have the distances hand. So it's calculating wise, it does not add anything, but it takes in account as the uh, weightage of as well. You also need to understand that every point of time, all the distances is calculated for all the points. So increasing k to 5 or 7 or 8 does not add that much complexity to a problem. So we should pick a relatively larger k. Okay. When we are working with just KNN on simple, then it's known as equality or equal distribution. And there is a weighted distance approach which takes in account the distance between the points as well. Always remember the weighted distance approach is a better approach, and k should not be very 3 or 5 or something, since it's complexity wise it doesn't increase anything. It can be larger like 10, 8 or 20 ideally. Okay. Also now there are few kinds of distances. Euclidean is basically x2 minus x1 into y2 minus y1 whole square, and this basically means the direct straight distance. Then there is a cosine similarity, which essentially if there are two vectors, if these are 2 points essentially, okay, like let's say there were 2 points, cosine similarity will go from 0 0 0, so origin, and it will measure the cosine. So it cosine is always between 0 and 90. So similarity at cos 0 is equal to 1 and cos 90 is equal to 0. So if they are perpendicular to each other, it is 0 similarity. If essentially they are same line, it becomes 1 similarity. Similarly, Manhattan and Jacquard are also some distances. Just Google them. But mostly Euclidean is used, and in certain datasets, cosine similarity is used, especially when you are looking at something which is non-scalable or non-negative type in nature. It's easier to do and it's faster. Other than that, again, there is the code, and again, the coding will go as an assignment because literally we are spoon feeding to a certain extent, and I want you guys to run the code on your own. So that will be it for this lecture, lecture 36, KNN, K nearest neighbor. Remember, distances. If your neighbors are rich, so are you. Most probably you are rich as well. That is the funda behind it. And take a relatively larger K. And there are two approaches, equiweighted and weighted distance approach. And I think the weighted distance approach clearly is the better approach most of the times. So that'll be all. Thank you guys.